Module 6, Finding the Probability of Events. Recall that the probability of an event can be approximated by taking the frequency of the desired outcome and divide that by the number of trials. So the frequency of the desired outcome divided by the number of trials. A random experiment is an experiment involving chance where the outcome cannot be predicted in advance. And last time we talked about this terminology, the list of all possible outcomes of a random experiment is called the sample space. Note that sometimes order matters when listing all possible outcomes, and sometimes it does not. And you'll be able to determine this based on the context of the problem. So in this example, I want you to list the sample spaces for each random experiment. So first, assume that a coin is tossed 2 times. All right, so the sample space, we're going to put it in set notation. So what might we come up with when a coin is tossed twice? Well, the first toss might be a heads, the second toss might be a head. Okay, again, the first toss could be head, the second toss could be a tail. The first toss could be a tail, the second toss could be a head. And then the last possibility is that we toss 2 tails. So that set would represent the sample space, the list of all possible outcomes. Let's look at our second example. A bowl contains 10 Twix and 10 Baby Ruth candy bars. You reach into the bowl without looking and pull out 3 candy bars at once. So for this particular one, the order that you list the 3 candy bars will not matter because we're not pulling one, then the second, then the last. We're pulling 3 at a time. So the question is, what 3 candy bars might we pull out of there? Well, we might pull out all 3 Twix. We might pull out 2 Twix and a Baby Ruth. We might pull out 1 Twix and 2 Baby Ruths. Or we could pull out all Baby Ruths. So again, since we reached in the bowl and pulled them all out at the same time, the order, so for example doing BBT, we don't need to list that because all of these groups of 3 were pulled out at the same time. Okay, for number 3, a homeowner association president, secretary, and treasurer are chosen randomly from 3 names in a hat: Jennifer, Lori, and Ken. The first name pulled will be president, the second secretary, and the last treasurer. So since the order matters in this case, we do need to make sure to list every permutation of those 3 names. So I'm going to use J for Jennifer, L for Lori, and K for Ken. So you might have Jennifer as president, Lori as secretary, and Ken as treasurer. So now you just have to make sure that you list these carefully and systematically so that you have every combination taken into account. So the way that I did this to help myself was that I started off with Jennifer as president, then I knew I would have to have Lori and then Ken, but then I could have the opposite of that, Ken then Lori. Then I did all options when Lori was president. Then I know that I would have to have Jennifer and then Ken, and then the opposite, Ken then Jennifer. So if you try to do it in a systematic way, that'll help you to make sure that you don't miss any of the combinations. Okay, so that would be the sample space. An event is a possible outcome of an experiment. And the event includes a subset of the sample space of the experiment. So an example, the event that you get at least one Twix bar includes which of the outcomes from example 2? Okay, well, example 2 gave us our sample space, but now we're interested in the event that we get at least one Twix bar. So if we want at least one Twix, that means we're going to have everything except for the case where we have all 3 baby Ruths. So this event would be 3 Twix bars, 2 Twix bars and a baby Ruth, and then a Twix bar and 2 baby Ruths. So this would be a subset of the sample space. In the last section, we learned we can estimate the probability of an event by dividing the frequency with which an event occurs by the total number of trials. Well, this is inefficient because we know that with the law of large numbers, you have to have a lot of trials in order to approach the true probability. Okay, so this is good to give us an idea, but we would not want that to be the method that we always have to follow. If all of the outcomes of a sample space are equally likely, then the probability of event A can be computed by taking the number of outcomes in A, the number of outcomes in event A, and divide that by the number of outcomes in the sample space S. Okay, divided by the number of outcomes in S. I don't think I mentioned it on the last page, but the sample space is often represented by the letter S. Well, let's look at an example of this. Okay, so the probability of event A is equal to the number of outcomes in event A divided by the total number of outcomes in the sample space. So for this example, a couple planning their family decides that they want 2 children. Underline the important parts here. Assuming that the chances of having a boy and girl are equal and not affected by prior children, and assuming no multiple births, what is the probability that the couple will have a boy and a girl? Well, the way that we can answer this is we can start off by writing the sample space. So this couple is going to have 2 children. So we want to write what are all of the ways that they could have 2 children. Well, they may have a boy, and then they might have another boy. The couple might have a boy, and then they could have a girl. Possible that they have the girl first, and then they could have a boy. And then lastly, they could have 2 girls. So that's our sample space, but we want to know what is the probability that the couple will have a boy and a girl. Okay, well, that event happens twice in our sample space, a boy and a girl. So that means that we have 2 divided by the total number in the sample space, which is 4, or 1/2. Going on to the next example. Chloe entered a contest and won. Her prize is that she can draw 2 balls out of a bag, and she will win the larger of the amounts on the ball. There are 3 balls in the bag with the following labels: $0, $1,000, and $100,000. If she pulls the $0 ball on her first draw, then she does not get an additional draw. If she pulls $0 on her second draw, then she will not be permitted to keep the money from her first draw. So we do not want to get the zero ball. What is the probability that she will win $100,000? Okay, so to figure this one out, we can write the sample space. Okay, so keep in mind that she gets 2 draws unless she gets the $0 ball, and that means she doesn't win anything and the game is over. Okay, so let's write our sample space. Okay, well, she could start off by drawing the 0 ball, and if she does, the game's over. Next, she could draw the $1,000 ball, and then on her second draw, she could get the 0 ball. Next, she could draw the 1,000 ball first, and then she could get the $100,000 ball next. Other possibility, she could draw the $100,000 ball, and then get the 0 ball. And lastly, she can draw the $100,000 ball first, and then draw the $1,000 ball. Okay, so that lists all of our possibilities, and we want the probability that she will win $100,000. Okay, so in which of these scenarios would she win the $100,000? Okay, well, she would win it in this case, and she'd also win it in the last case. So the probability would be 2 out of a possible 1, 2, 3, 4, 5. And that would be our answer. And it's fine to leave it as a fraction. You can put it in decimal form if you wish. Usually the question will specify the form they want you to put your probability in. Now we're going to look at some probability rules. This first rule we saw in the last module. The probability of an event A is always going to lie between the numbers 0 and 1. Secondly, the probability of getting something in the sample space is going to be 1. Since the sample space lists all possible outcomes, you know you're going to get something in that sample space. So it's guaranteed, which is what the 1 represents. So let me just put in parentheses a reminder that S is the sample space. Okay, next, some terminology that you need to be familiar with. If we have the event that A does not occur, that's called the complement of A. So if A does not occur, that's called the complement of A. That's everything without A. So the probability of not A is going to be 1 minus the probability of A. Okay, so let's look at some examples of this. Suppose you roll a dice. What is the probability that you will not roll a 4? Okay, so often when it's stated in the negative, it's a little bit harder to digest. So we can use our complement rule and rewrite this. So the probability that we do not roll a 4 is the same thing as 1 minus the probability that we do roll a 4. So this is 1 minus, well, what's the probability that you would roll a 4 on a dice? It would be 1 out of 6. So 1 minus 1/6 would give us 5/6. Let's go on to number 2. For the example with Chloe above, the one who was playing the game, withdrawing the balls with money, what is the probability that she will not win $100,000? Well, using our complement rule, I know that this is the same thing as 1 minus the probability that she wins $100,000. And we actually found that value. The probability that she wins $100,000 is 2 out of 5. So to answer this question, we want 1 minus 2 out of 5, or 3 out of 5. And let's save this as we go along. Here, our third example. The following table shows the probability of obtaining a doctoral degree in a particular area of study from U.S. universities in 2005 by area of study. Fill in the question mark. So we see the probability of obtaining a doctorate in engineering was 0.148, physical sciences 0.1, even smaller in math 0.028, and we're trying to figure out the probability of obtaining a doctorate in education. Okay, well, to do that, assuming that these are all of the areas that doctorates were obtained in, the probability of getting a doctorate in education is the same as its complement, 1 minus the probability of getting a doctorate that's not education. Okay, well, how do we find the probability of getting a doctorate that's not in education? We're going to add all of those together. So this will be the sum of the probabilities that are not education. Okay, so we keep the 1 minus, if you add all of those together, you should end up with 0.856. So we end up with 0.144 for our answer.